it was very frustrating to get this template to work. They send all my pictures red. So.
Where is this? It's cleaner?
No, it's
Static?
yes, latex.
Looks nice.
Okay, so thank you for allowing me to talk. I've had a lot of fun at this program, and I'm going to talk about something which may seem a bit orthogonal to what the title of the program is, but I promise you it's not, and I guess you'll have to wait and see. So it's joint work with Tadahiro Oh, Nikolay Tzvetkov and Hendrik, and it's on quasi-invariant Gaussian measures for the 3D nonlinear wave equation. So what's the problem? Oh, I can use the clicker, right?
Mm-hmm.
Okay. So at the center stage of everything is this nonlinear PDE. It's how do you point? Like this? Okay. So it's the linear wave operator applied to U is minus U cubed. So it's called the cubic because of the nonlinearity, and defocusing because of the sign. And we're interested in the Cauchy problem for this on the 3 torus, so in 3 dimensions. And this PDE has a natural Hamiltonian structure, which means that if you write V as dtu, then you can write a system of equations, and this conserves the Hamiltonian E of U in the sense that if you take the time derivative of this and U bar, or whatever you want to call it, is a solution, then this is a 0. The derivative is 0. So this energy is conserved along your trajectories, your solutions, and this means that as long as sigma.
What's V? V is the.
V is dtu. Yes,
Yeah,
it's the velocity or momentum or whatever you want to call it. So I mean, it has a very natural product structure. So you want to pose this in these product Sobolev spaces, which I called H sigma bar. And okay, it's natural. H sigma bar just means H sigma in the U coordinate, and then sigma minus 1 in the V coordinate. And we're going to work within homogeneous spaces. And this energy it's classical that if you have sigma greater than 1, then you use this energy to give you global well-posedness in these spaces. And so you have a global in time flow. So global in time is because it's reversible. So you have a well-defined deterministic flow on these spaces for all t. And the main question underlying this talk is how does this flow transport the natural Gaussian measures on these spaces? And we'll be really interested in the high regularity theory. Suppose from a different PDE perspective is, suppose we start our PDE with random initial data, then what can we say? So random initial data drawn from Gaussian measures, which I'll define in a second. What can we say about the solutions? So what's our contribution to this question? So this is a theorem which is on the archive as of 16 hours ago or something, and it says that if S is an even integer greater than 4, then the Gaussian measure with Cameron-Martin space Hs plus 1, which means that the density of the measure looks like this, is quasi-invariant under the flow of the equation, which just means under the flow of full time t. So just in case you need a little cheat sheet, by Gaussian measure of Cameron-Martin space Hs plus 1, it's this guy, so it's realized on H sigma. So it's realized on H sigma for. You should think of this measure living on H sigma, where sigma is less than S minus a half. So the measures I call US live on. Okay, and what is quasi-invariance? Well, first
You are in one dimension.
no 3D. So yeah, we're on the 3D torus.
There is a reason why you look in 3D.
Yes, because 2D is done and 3D is open.
No, but you can look at any dimension, or at some point it breaks down.
Well, our techniques work for 2D and 1D. Higher dimensions I'll discuss in a bit. I think it's, well, we'll see.
I think that also the equation has some problems.
Yes.
Bigger than 3.
Yeah, I don't know what the nonlinearity.
Yeah.
So at some point it
there is
becomes.
some links between
Sorry?
the dimension and the 3 of the
Yes, so in dimension 3, I think you need it to be 7, and then it's still posed, or something. Then it's energy critical, whatever they call it. But I don't know what. I think in dimension 4 you can still do cubic, but okay, don't quote me on that. Right. So So invariant is the stronger property. It's that if you have just a measure and some measurable transformation on the same measure space, then the push forward is itself. And quasi-invariance is kind of the next best thing, that the zero sets are identical, so it's mutually absolutely continuous with respect to mu. So what we show is that the zero sets of the solution at time t are the same as the zero sets of the initial data, right? Okay, so why should you care about this result? Well, first of all, so these are more PDE perspectives, but and I'll come to it. But maybe just from the viewpoint of transport of measures, you know that there's this classical result that if you just look at vector fields which shift it linearly, then you have to go in the direction of zero Cameron-Martin space, which have measure 0 in the space that's realized. But what this does is it provides a complete trajectory, a very nonlinear trajectory, along which these flows are quasi-invariant. So that's one nice, I think, point of view. But I think I want to kind of stay with the PD aspect and say, okay, well, this kind of comes from the fact that in the linear equation, the linear wave equation is integrable in the sense that it admits a hierarchy or lots and lots of conservation laws. So, okay, there's some issues with the zero Fourier norm, but let's just Fourier mode, but we can just ignore it and just kind of pretend that these measures, these US measures, are actually invariant under the wave equation, and okay, and you don't have a restriction on s being an even integer. And you can kind of see this because the linear wave operator is a rotation, can be viewed on a rotation map on the Fourier modes, and you know that Gaussian measures are invariant under these rotations. So then we ask the question of, okay, so the linear dynamics admits this many conservation laws and has this many invariant measures. What happens when we perturb this by nonlinearity? And our result is not a global result by saying, okay, you don't expect invariance to hold, it's wrong. But you still retain the small scale properties, so the measure 0 sets of the flow, of the linear flow. And this has an implication for regularity theory for these equations. So even for the linear wave equation, so in the parabolic world that your differential operators have a smoothing effect, but for the wave equations this is not true. They have a persistence of the regularity on L2 scale, L2 based Sobolev spaces. So in other words, they map HS and HS. But then if you ask the question, what if I look at WSP regularity? Well, it's just not true that it maps WSP to WSP without some derivative losses. So these are works by Stein and Soggy and Littman. And then, okay, you can kind of think that if we now have a nonlinear equation, you expect it to have the same persistence of regularity effects as the linear equation, because you can write the solution map as linear part plus some smoother. But what this result says is, that the Gaussian measure, that almost surely these sample paths belong to Holder spaces or WSP spaces, as long as you're or W sigma P spaces, as long as you have this condition. And so what this says is that this higher order regularity is preserved along the flow. So I think it's quite a nice implication. And then there are two. This one I want to spend less time on, but there's a connection to statistical wave turbulence, and it's a very small connection, and it's not very. We don't do much in this direction. But in statistical wave turbulence, if you remember, I said you can view this as kind of randomizing your initial data. Well, then you're interested in the expectation of your Fourier coefficients at time t, and you want to look at how these evolve in time. So you can kind of see that, okay, we're interested, if we're interested in how these evolve, then this corresponds to how we're interested in properties of the Radon-Nikodym derivative of the push-forward measure under this, right? And so what do we show in this direction? The answer is not much, because this to rigorously justify these things, you need that the Radon-Nikodym derivative of the flow is square integrable, and we only show it's in L1. But I think it's an interesting connection, and it was pointed out to Tadahiro and Nikolay in the 2D case. And okay, it might be a possible future direction. But I think for this workshop, I think it's a really nice result because of the proof, and there's something surprising, but I won't spoil the surprise. We'll see it in a few slides' time. Okay, so is everyone happy with the statement of the theorem and why you care about it? Yes?
I have a basic question. I understand that it doesn't help for the regularity question you're interested in, but should there be an invariant measure?
Well, okay, we'll see, but the invariant, I guess the invariant measure is kind of e to the minus this guy, right?
Right.
Yeah.
So that.
But we're interested in higher order invariant measures. So, you know, the linear wave equation, forget this quartic term, has invariant measure this, but it also has invariant measures where the E is kind of an ES, where you take the higher order Sobolev norms. But this is not true for the nonlinear wave equation. You have to add a correction term, and this will feature soon, yeah.
It's by 4.
Sorry?
It's by 4, the value.
Yeah, exactly. That was my question.
Right. Yes, but we're interested in high regularity.
Right. Okay, so that's the point. That's
So-
why. So that's easy to see that this is the invariant one. I mean.
Yes, it's very easy to see. Okay, so
What do you mean?
Well, I mean that this is the.
it's easy to see that the energy, you know, the energy with the four.
I mean, it's by 4.
Yeah.
It's not easy. You have to define. I mean,
Yeah.
I don't know.
Oh, well,
It's
No,
easy
on a
to
formal
see, but
level.
very hard to say what it is.
Even if you had noise and dissipation, I would not know how to do it. Yeah.
Right, but okay, if you truncate, then it's certainly true. Okay. That's
Yeah, you can truncate in such a way. that-
Yes.
You can look at the lattice wave equation, right?
No, but you have to modify the equation.
yes, you do. You have to add a projector.
Yeah,
Onto the
it's,
nonlinearity.
yeah,
Yes, yeah, that's correct. Okay, so where does this fit in with our results? So the 2D paper was only proven last year, and it's going to appear in GEM soon. And their analysis is pretty delicate. It's a multilinear analysis, and they get the same qualitative result as our result, but there's a slight difference in the sense that they get something slightly more quantitative, but not for the Radon-Nikodym derivative of this. So you should think of it as an improvement on this, but we do lose something. Because the techniques of this just do not extend to 3D at all. And so we need to do something new, but you can kind of see that you lose something in passage 3D. And it's one of the, it's a kind of an addition to a series of recent results in these establishing of quasi-invariants for Gaussian measures for Hamiltonian PDEs, which is, I think, started in this paper by Nikolay. At least this framework that we use. So there's a load more papers that I didn't quote because I didn't want to bore you with the number, but it's in the paper you'll see a huge list, and I think it's a really exciting area at the moment. So what are the future directions for this? So there are these two are a bit more important, but let me just comment on some less important things, which is, so here we have a restriction that s is an even integer, and the greater than 4 is important, but it's an even integer, and this is just because then you have classical differential operators, and you can apply Leibniz rules. So it may be interesting to do this for all this, because for the wave equation, you don't have this integral assumption on s. Okay, but what's the kind of the more interesting directions? So I think one is to get more information on this Radon-Nikodym derivative. So for example, higher order integrability, which would have applications there. And also possibly doing these things in higher dimensions. Then you have to be careful about the kind of the size of the order of the nonlinearity, and you have to be worried about issues of global existence. The final future direction, which I find really exciting, and maybe Ben, you also find it exciting, is to study this in the context of low regularity solutions. So for low regularity solutions, by that I mean, okay, s less than 4, fine, but I mean even going to this threshold where these equations are, it's going below this guy. So where you get deterministic ill-posedness results, but probabilistic well-posedness. So then the flows are constructed stochastically. And it would be a very interesting question, but I think it's probably far out of reach. Okay, so is everyone now convinced of what the problem is and what we do and why you care and also what other people did? Yeah? So let's see a little bit of the proof. I probably, how long do I have? Like 10 minutes or?
Well, you've got 5 minutes more than you think you have in terms of having started.
So about 15?
Yeah.
Okay, that's good.
I
So
have a silly
yes.
question, so I pose it now, so it becomes silly. Why you call the measure mu s, which has nothing to do either with the support or with the Cameron-Martins?
Yes, it does. Mu s is s plus 1. It's just because of some, okay. Well, I mean, we just have to stick with the convention of the previous papers. That's the only reason. Okay, yeah, fine, s is s. But
I mean, there would be mu s plus 1.
yes. Okay. Yes. Right. So let's look at some elements of the proof, and I think this might be somewhat exciting to all of you. Maybe I do this. Okay. So let's kind of just forget that we're dealing with measures, and let's just do some standard ODE stuff. So suppose we have the differential inequality that for all p greater than 2 we have this. So the derivative of x is bounded by p times x to the 1 minus 1 of p. Okay, so you should really think of x as the measure evolution, but this is really an ODE result. So then if you take the derivative of x to the 1 over p, it's bounded. And you can ask, okay, does the power of p matter? And the answer is yes. So if you kind of put a p to the beta there, and you do this, then if beta is less than 1, this is good, it contracts. If beta is 1, it's this. If beta is greater than 1, it explodes and it's useless. But, okay, so we will want to work with p equals 1. So here, if you integrate out from 0 to t, you get a bound on the measure evolution. So you get that x of t is bounded by something huge, if you think of p as very large. So p is infinity, well, almost. Then this is very huge. But then if we choose our time small enough, this is very small. Now, since we're interested in absolute continuity, you should think of x naught as 0. So this is 0 anyway, even though p is infinity. And so this is very small. And so the idea of this inequality is to kind of say that if you start with 0, you are 0. And then you want this inequality to hold for all times, and this p and this constant not to depend on time, so you can kind of piece it together and obtain global quasi-invariance. So do you understand this kind of globalization? Yes? Okay.
So you're considering progressively smoother, or what is the p in this this argument? I mean, you're going into LPs of.
You'll see. Yeah. So I've just said that if you have this, then you have quasi-invariance all times, and it's not clear immediately why this is a natural estimate, but it is, and I'll show you why. Yeah.
Well, wait a second. So you're trying to get quasi-invariance for all time, right? So
Yes.
So you're going to do some intersection of LP spaces or something in order to make.
No.
No, I didn't quite understand. I mean, as you make p smaller,
P is not small. P is huge.
P, yeah, one way of doing it makes the time of existence very small.
Yes.
Right.
But the point is that this constant and this p doesn't depend on time. So if you have quasi-invariance for short times, you can kind of restart your flow.
Ah, okay.
So you kind of you have quasi-invariance for these times, but then you restart your flow here, and then you just kind of piece it together.
Yeah, I mean, this estimate is like saying I have an estimate like dtx is x log x.
Dtx is x log.
When p is
Yeah.
because I think this I understand. So because this is the boundary where you can prove still uniqueness for objects. Where you don't have Lipschitz, you have a smaller Lipschitz, but essentially this smallness has to be logarithmic. This is in your argument. At the end, you have to take p to infinity,
Yes.
which corresponds to have like, I think, x log x there, something like that. Because you see, it is a bit less than 1, but you see when you send p to infinity, in the numerator, I mean, this is a ODE which is not Lipschitz.
Yes, I agree.
But if you have this precise estimate, it's like a
I
x log x
behavior. Okay, so Roman, we're just discussing some ideas of the proof for this result. But hopefully you know this result because...
Yeah, I should.
Okay, good. So we were just discussing that if you have this differential inequality, then you can from this you can establish small time quasi-invariance, but then you can then globalize it by just kind of piecing together the flow. So why is this differential inequality natural when you have a measure evolution? It's because of this. So if you look at the derivative of this measure, then maybe I skipped a step here and it's impossible to understand, but hopefully not. So imagine the dt outside and you have the phi of t here. Then what you do is you do a change of variables, you put your phi of t into the u, but you know that for Hamiltonian systems, the Jacobian of this transformation is 1. So therefore you don't pay over anything. And so you get a time-independent guy here. You get the derivative falling on this energy, and so you have the derivative of the energy e to the blah. Does everyone understand that? I hope it's somewhat clear. Maybe I should add another line for when I do this again. Yeah? Okay, and then here...
I understand the change of variable, but why you have phi t0 there?
Oh, because you use... Okay, so we would like this inequality to hold for all times, not just time t equals 0. So we'd like to take the derivative at t equals t naught, for example. Okay? But then what we do is we use the flow property of this and say, okay, then we can just kind of fix t naught and consider t after t naught. And so the derivative on this falls at time t equals 0. And we know at time t equals 0, this is distributed according to a Gaussian, so we have access to Gaussian calculus. Or Gaussian estimates, yeah? Okay, so then we take the LP norm we use Hölder, and you see the x to the 1 minus 1 over p, the mu s of this guy to the 1 minus 1 over p, and then you see a constant which a priori doesn't really look like it's going to behave like sublinear in p. But you see that it's only established at time t equals 0. Okay?
You could take exponential or not. I mean, instead of doing LP, you do like exponential and log. You send p to infinity right now.
Well, you mean once we have this?
No,
we haven't
you are doing some older inequality. No? You can do it with two Young functions, so you can use exponential and log.
I don't understand.
Okay.
No, but we can discuss it after I didn't. Okay, so it suggests that we need to establish this guy, but then the question is it possible for nonlinear PDE? And this relates to the question Roland asked, because it's not very natural that if you have a nonlinearity that this, I think anyway, that this holds. It holds in one case, I think, so far. But let's do the calculation, it's not that hard. So if you take the derivative, so here we're going to pretend that inhomogeneous is homogeneous, which is not such a bad thing to do. So if you take the derivative of this Sobolev energy, then you're going to get the derivative of u, the s plus 1 derivatives of u, s plus 1 derivatives of v, and then this guy. And then here we use that u solves the equation, and u and v solve the equation. So then we get this term which comes precisely due to the presence of the cubic nonlinearity. So if this was a linear equation, this would be 0. And then you get that this energy would be, the derivative would be 0, and so by this formal argument here, you get that the derivative would be 0, and so it's conserved. It's an invariant measure, which is a good reality check. Okay, but here we use that s as a differential, ds as a differential operator. This is where one of our assumptions on s comes in. So to leading order, it's this guy, and then you have lower order terms, which if you use fractional Leibniz estimates, you don't get explicit forms for these guys, but the leading order term is still the same. So you have dsv, dsu, u squared, and in light of this regularity condition here, you're going to have that this belongs into C minus 3/2, and this belongs into C minus 1/2, and this, well, okay, this is S minus 1/2 minus. So this is a pretty scary object from the point of view of regularity, but also a pretty scary object from the point of view of having a sublinear dependence on P, because this belongs to the fourth chaos, and so you expect an estimate which grows in P squared. Okay, but let's deal with the irregularity issue. You can integrate by parts, and then you get these terms. So you get the derivative of ds u squared, and the derivative of this. This is somewhat better because this is in C minus 1. And this is okay because how do we treat a term with the time derivative? We just shove it back into this energy, and then the idea is you don't treat these kind of Gaussian measures, you treat a weighted Gaussian.
So which term did you integrate by parts?
The leading order term. This guy.
That one?
Yes.
Okay. Oh yeah, all right.
And then we see, okay, this is not so scary anymore because we know how to construct, well, okay, maybe we don't, but we do, construct measures with singularities like this. It's kind of like 5,4, and we need to introduce a renormalization. But then you might be worried, and also even this term, if you renormalize it, it's fairly well behaved. But then you might be a bit scared because, okay, do we have to introduce renormalizations at the level of the equation? But the point is no, because if you take the derivative of this infinity, then it's precisely this infinity. And so you can simultaneously renormalize both of these without changing the equation. So I think this is really surprising that in this high regularity theory, you have the presence of renormalization. And so this is why I think it's a pretty cute proof, and well, this is not the proof, but this is a pretty cute technique, and I think maybe you guys will like it. Okay, but this now seems a bit more sensible, and this is my final. I think this is the final thing I want to say, that this kind of gives you the problem that, okay, ignore the grey people here, but we want to now construct the measure with this weight. Okay, and we want to establish a renormalized energy estimate. So this ES, sorry, should be ES plus HS. So it should be the weight plus the Gaussian part. So we boil down our problem into two parts. So we construct this measure and establish the renormalized energy estimate. And we do this in the spirit of Max and Barashkov's approach via this variational formula. But there's a little technical problem that we don't know whether this term is good enough to control large-scale behavior in U. So we use that the Hamiltonian, the Hamiltonian of the equation is invariant, and we can smuggle in a U to the 4. So these, yes?
Where's the second renormalization that you had?
No, because this renormalization is on the level of the time derivative, so it's always with the time derivative. This renormalization is kind of shoved in up there and is kept into the measure. Yeah, do you understand?
It's changing the measure.
It's changing the measure. Yeah.
This,
So if you imagine we had all this blah blah, here we wouldn't have this measure, we'd have, so this energy, we'd have the energy plus the nonlinear correction term. And this would be this thing, plus the nonlinear correction term. And then we have to do everything with respect to this weighted measure. That's okay. So then how do we construct this measure? I think these measures are pretty interesting because they look formally like 5,4 in the sense that they're quartic, but they're not, because you just need some trivial renormalization even in 3D. And also this means that the higher nonlinearity problem is tractable because you don't have to worry about these measures being non-constructible. So for example, instead of a cubic nonlinearity, I think possibly if we take a quintic nonlinearity, maybe there are not too many issues. Okay, the second problem is to establish the renormalized energy estimate, and then we want this sublinear behavior in P. This is difficult, and it requires some sort of deterministic regularity to compete against the stochastic singularities. And that I don't have time to go into, but that's a different story, and that's very interesting. So this is the summary of the approach. You have to construct this weighted Gaussian measure, then you derive this differential inequality. Okay, and as soon as you have this renormalized energy estimate, you can then kind of get small time quasi-invariance and then global by this Udovich argument. Yeah, so I think that's a nice place to stop. So I'm going to stop there, but thank you for listening, and if you have any questions, then yeah.
I don't want the whole argument, but just what's
It's this thing. So it's that going from this inequality to local and time quasi-invariance and then global.
Yeah, I think which is not about quasi-invariance, is about
No, it's about Euler
equation.
Yeah.
Yeah, but the problem is that the vector field is now.
Yeah, okay. I think I understand your earlier question. Yeah.
And then I go back because now, yeah, you in the estimate, now you go forward. The point is that you need not the p power, but the exponential integrability of this guy, of the time derivative.
You the exponential.
No, go down.
Yes, exactly.
You go down.
Where? This guy.
Yeah, I claim that it's enough
Oh!
to prove that this is exponentially
But that's the
integrable.
same as the power p.
Yeah, but you don't need the power p. You just
That's equivalent.
yeah. But
No,
my
okay,
point was that because Udovich estimate at the beginning is epsilon log epsilon.
Okay.
Yeah, but then if you need just to prove the exponential integrability of this guy, you can still use the variational method to do that.
The variation. You mean?
I mean the method I have with Paraskov. Since you already use for other things, you can also use it for control distance.
You mean this? The derivative of this new energy. Okay, that's.
Because as soon as in the
No, but do
exponential,
you-
it's easier. No, if you write the exponential, there is no p around. This p means only the exponential. So when you write this, it's just, I want to prove that the time derivative is, the exponential of the time derivative is integrable,
Yes.
then you can use the method directly.
No, but Max, it's a bit different. The issue here is that this time derivative ends up being a quartic expression in U, and a quartic expression would a priori only have kind of stretched exponential with the exponent.
No, because it depends what are the good terms you have to balance them.
But there's no good terms there. You just,
But it introduces later, of course, in this
no,
expression.
but that's a
then-
different part of the argument. Here it's really with the Gaussian measure. So use a quartic expression and use Gaussian for that
So
estimate.
then I didn't understood what you did in the next slide, sorry. So you introduce a new measure.
Yes. Yes.
Where it appears.
So here the new measure is this guy.
Yeah, so, yeah, and then he uses the new measure in the estimate, you said.
No, that's the nu down there. So it's the tensor nu. So
This is new. This is the Gaussian guy here. This is sorry. I called new. Okay, maybe I should explain this. When we added the Hamiltonian, we take all the quadratic parts and we add it into the Gaussian measure, and we kind of tilt our Gaussian measure, so mu becomes nu.
Okay, so what is the role of rho?
Rho?
Yeah, because it never appears anywhere else.
No, it does.
Yeah,
So-
I could imagine that.
Yes. So rho comes here, right? So we kind of we imagine we replace, or maybe do I mean rho? No. Yeah. So okay, rho appears here. You put it instead of this guy. You put the full weighted energy here, right?
Okay, so
Yeah.
the process is not Gaussian anymore. The measure
The
is-
measure is not. You prove this inequality for a non-Gaussian measure.
Yeah, so that's what was my argument. I mean, you change. I mean, I don't know. My understanding is that okay, you just use a different measure. You use rho instead of mu
Yes.
because you
But-
need to control more terms.
Yes, but that's not enough. So in this, to go from this line to this line, we use growth norms on this guy coming from the nonlinear dynamics. So there's an extra step here in the quasi-invariance proof, because otherwise we don't have any deterministic regularity to kind of compete against it. Well, at least in doing it this way.
I should have read it. Okay, thank you.
Anything else?